So we started the second device called bipolar junction transistor. We have seen how bipolar junction transistor shows in transistor action. What is in transistor action? We discussed the device structure of bipolar junction transistor. In the last lecture, we discussed the small signal analysis and a very important concept called base width modulation. So in this particular lecture, we'll cover two different things. One is BJT circuits, because once you have a device, you will make a circuit with this device, and there are three basic circuits that one can make using BJT, which is common base, commen-emitter, commen-collector. We will see those BJT circuits and what is the circuit configuration for these three types of circuits, why they are called common base, commen-emitter, commen-collector. By the way, base, emitter and collector are the three regions of the BJT itself. So you must have already learned that in the previous lectures. So this is what we will study, and then we will go to BJT output characteristics, meaning what is the IV characteristics associated with BJT. So that we will discuss in this particular lecture. What is x-axis, what is y-axis in that output characteristics, which one we take as x-axis, that is the voltage, which current we take in the y-axis, that is the current consideration, and how it looks, what are the different regions in the output characteristics, why output characteristics is important, where do we actually apply BJT in that particular zone, is something that we will discuss in this lecture. So let us start the lecture and see these concepts.
So today we will start with the Venn diagram of BJT under zero bias. So if you look at the Venn diagram, it will be similar to that of the PN junctions, but in this case we have two PN junctions. One is the emitter junction, another one is the collector junction. So to start drawing the Venn diagram, we should first consider the Fermi level that we already have seen during the analysis of PN junction. So it's better to start with the Fermi level, which is constant. Now you have two different junctions. One is emitter base junction, or you can call it emitter junction, and then you have base collector junction, or you can call it collector junction. And we also know that the doping level in the emitter junction is the highest, which is shown as P++. Then you have base region where it is N+, and then the lowest doping is in the collector, which is shown as P. Now in this case, what matters is the difference between your EF and EV, right? So the best way to analyze the energy band diagram is to first figure out the difference between EF and EV in case of emitter, which should be the lowest because the doping level is higher. Then the difference between EC and EF in the base region, which should be a bit higher compared to the emitter. Then you have the difference between EV and EF in the collector, which should be even higher. And then you know that the difference between EC and EV is nothing but your band gap. Then just draw the corresponding EC and EV in all the regions. Thereafter, you join the EC and EV in each of these locations. Now we know that in emitter junction, the depletion width would be less than that of the collector junction that we already have seen, and based on that, we'll get an energy band diagram which looks like this under equilibrium. In this case, we haven't applied any bias. Now, if you put bias in this device, so definitely your energy band diagram also will change, and the same will look like this, wherein you will have a huge barrier in case of collector junction because your base collector junction is reverse biased, and you'll find that the built-in potential here will reduce by a amount of forward bias voltage, and the entire picture will look like this. So your base collector junction, as the junction is in reverse bias, the built-in potential will be psi 0 plus the reverse bias voltage, and in case of emitter junction, as this junction is in forward bias, the built-in potential will be the built-in potential in equilibrium minus the forward bias voltage. So this is the energy band diagram of a BJT under the biasing condition where BJT acts as an amplifier. So this is the condition where BJT acts as an amplifier. That means emitter junction is forward bias, collector junction is reverse biased. Okay. So if you put the entire BJT in amplifier operation, the band diagram will look like this. So I repeat, there is nothing called BJT in forward bias. So I think I have mentioned previously. So this statement is not valid. Rather, you say BJT as amplifier wherein your emitter junction is forward biased and collector junction is reverse biased. Now from the analysis of band diagram, you also can very easily draw when both the junctions are in reverse bias or both the junctions are in forward bias. So although this is the situation where most of the BJTs are operating. Okay. So these are the band diagram of BJT. Now we have seen different BJT biasing. Now there are different BJT configurations also which generally people use for different purposes. One I already have explained or discussed, which is common base configuration, wherein your base is common to both input and output side. Similarly, you also have a configuration which is known as common-emitter configuration, where the emitter is common with input and output both. And similarly, you will also have common-collector configuration. Now, these type of configurations are more described in analog circuit courses. You can check the analog circuit lectures and you will find a circuit description of these configurations. However, to make a connection between the circuit and device, I am showing you the configurations where I have shown the entire circuit using a schematic device. But in circuit, you will find diagrams like this wherein people use the symbol of BJT. So this is what the common base circuit will look like for PNP transistors. This is the common emitter circuit and this is the common collector circuit. Now if you look at the common emitter circuit, for example, this particular circuit also is practically implemented using this form, wherein you remove the extra power or extra voltage source and provide this voltage using a voltage divider circuit connected to the voltage source VCC. So this is what your VCC. So what others do is they use a voltage divider circuit R1, R2, and then they connect this with VCC, and then the voltage drop across R2, which is nothing but R2 divided by R1 plus R2 into VCC, That is what they apply across the base. So in this case, you don't need an extra voltage source connected here. Similarly, you also use some capacitors to decouple the AC and DC signal. So this is your small voltage that you apply for, say, amplification, and this is your common emitter circuit that you will find in practical use mostly. Now, if you look at the common emitter circuit that I have shown, that also is not the one which is very reliable, because your base emitter junction or the junctions in the BJT are very sensitive towards temperature. So if there is a change in temperature, you will find the effect in the junction voltage. So in all the cases, you will find that temperature will play an important role, and temperature will increase because in the device there are currents, and current will dissipate inside the device as a power, and that will generate heat. So that heat will definitely increase the temperature in different junctions. Now, in such a situation, what people generally do, they try to maintain the current, or they try to make the level of the current constant throughout. In that case, you will find that the change in voltage is very small, which can be understood by this plot. Here I have drawn two different forward bias junction plots because your EB junction is in forward bias. So I have drawn two forward junction plots wherein you can see that if your T2 is greater than T1, your plot will look like this. Now, for a particular voltage in two different temperatures, you can see that the change in current is significant. It's a very high change in current. So if you maintain the voltage, the change in the current will be very high due to the temperature. However, if you maintain the current, then your change in voltage is not that significant. So it is better to maintain the current or to control the current, and that is why you will find generally people use an emitter resistor here in order to control the current. So the idea is to make the current constant, and as you have an emitter resistor, that will help to maintain the current in the circuit, and that is why in many of the practical circuits you will find an RE is attached to it. However, it also has an explanation from the circuit perspective that again has been discussed in the analog circuit course. But from the device perspective, I am saying why we try to maintain or try to keep the current constant or try to control the current rather than controlling the voltage, because controlling voltage anyways will not help. In forward bias condition, the change in the current due to the temperature for a single voltage is very, very high. Apart from this, we also use a bypass capacitor here again to decouple or to short the AC through this particular resistor. Again, I am saying that the circuit description of this particular configuration is already given in the analog circuit course. Here, the idea is to connect the circuit with the device, and the explanation which is required from the device perspective, that is what I have just given. Now, let us see the forward bias characteristics and try to analyze this one. Now, the forward bias characteristics, it's not the forward bias characteristics, I'm sorry again, it's the output characteristics. So, the output characteristics of BJT will look something like this. So, the output characteristics shows that initially the current versus voltage. In this case, the current is the emitter current and the voltage is VCE, that is collector to emitter voltage. And we are drawing this output characteristics for the common-emitter configuration. So you have collector current and you have collector to emitter voltage. Now, in this case, you can see that initially the relation between the output current and output voltage is linear, and then the current will kind of decrease and will sort of saturate. So it's not exactly saturating, it's not constant. There is a slope associated with that, but it's sort of saturating. Now, in this case, what you should note is that the current values here is actually negative. It should be negative because here you can see the current is going out of the terminal. Now, by convention, we consider the current going out of the terminal as negative. So, the IC should be negative. Your IB also should be negative because IB also going out of the terminal. And then your VCE, the voltage you apply, is also should be negative. However, we only consider the magnitude in this diagram. Okay. Now, based on this particular output characteristics behavior, we consider three different regions in BJT output characteristics. One region is called saturation region, another one is the active region where we generally operate our device, and then we have a cutoff region here. Now we will try to understand the output characteristics of BJT. Now let us start with the VC equal to 0 condition, that is from here. Let us see what is the physics or what is the phenomena going on when VEC is equal to 0. Now when your VEC is equal to 0, your emitter base voltage and the collector base voltage will be equal, and they should be opposite in nature, and then only they will cancel out and your VEC will be equal to 0. So in this case, your emitter and collector is shorted. That is why your VEC is equal to 0, and this particular voltages will be equal in magnitude and should be opposite in nature. Now let us again draw the excess carrier concentration plot. So the excess carrier concentration plot will look something like this. So this is your excess carrier concentration in the emitter region, which will be spread out throughout the emitter. Usually we take fairly long emitter and collector region, and your base region is very thin. So usually the dimension is around 1 to 2 micron. However, these regions will be tens of microns or more than that. Now this is the excess carrier concentration plot in the emitter region. We already have seen. Your excess carrier concentration in the base region will look something like this, because the voltage associated with emitter junction and collector junction is same, and that's why you should find the excess carrier concentration in both the junctions should be equal. So the plot will look something like this. Similarly, in the collector region, you will find the excess carrier concentration is of this type. Now, one thing you should note that the entire plot is not drawn in scale. Usually, or if you draw it in scale, you'll find that the excess carrier concentration at this point should be at least 10 times smaller than that of this one, because the doping level is higher in emitter region. And similarly, the excess carrier concentration here should be 10 times more than this one. Again, the doping level in base region is higher than that of collector region, and the difference between the doping levels is of this order. So if you draw it in scale, probably this excess carrier concentration will not be that visible. So just for a representation, I am drawing it in this way. Now this is how your excess carrier concentration will look like. Now if you look at the flow diagram now in this case, you'll find that the holes are getting injected from emitter to base region, and similarly you'll find that holes are getting injected to collector to base region as well. If you see the slope here, it will be much clearer that there will be a hole current from collector to base and as well as emitter to base region. And similarly, you will also find the electron currents are from base to collector region as shown using this dotted line, and also from the base to emitter region. These electrons are getting injected by the base current, right? Now they will recombine in the base region, collector region and emitter region. However, we know that the base is very, very thin compared to the collector and emitter, so we can ignore this recombination. In modern transistors, we can ignore the recombination in the base region, and thus your flow diagram will look something like this. Now we know that the current in the emitter side will be less compared to the collector side, because the emitter side has a huge doping compared to the collector side, and thus you can ignore the current in the emitter side, because the current in the collector side will be much higher. So you ignore this part. So your flow diagram will look something like this, and you will find that at VEC is equal to 0, you have a very small current which is equal to IB, because in this case your IC is equal to IB. However, if you look at the output characteristics, you will see that the plot starts from VEC is equal to 0 and the current there is positive, but in practice you will find at VEC is equal to 0 or VC equal to 0, the current is not actually positive. The current is going inside the terminal in this direction, that is inside the terminal, and it is actually negative and is equal to IB. So this is where the output characteristics should start, and then it will rise. So our next target point is when IC is equal to 0. Let us find the value of VEC when IC is equal to 0. For that purpose, what we have done, we added a voltage source in between emitter and collector junction. Now the moment you have a voltage source, and if you start increasing the voltage, then your forward bias in collector junction or base collector junction will reduce with the increase in VEC. Now your VEC is nothing but VEB minus VCB, that is VEB minus VCB. So this is what your VEC value is. Now if your VCB is less than VEB, you will find the excess carrier concentration will be something like this, where this will not change, the emitter, the excess carrier concentration in the emitter region. In the base region, obviously as this potential difference is now not same in both the junction, and in VEB you have a higher potential, so definitely excess carrier concentration will be higher in this case, and in the collector junction it will be lower, and similarly the excess carrier concentration in the collector region will be something like this. Now the carrier flow diagram will be similar to the one that we have described, with few changes. The first change is, now the hole will be injected from emitter to base region. A portion will recombine, and then the rest will go to the collector junction. And for electrons also, the electrons will now go from base to collector junction as well as from base to emitter junction, the way we described previously. And the recombination in the base region will be very, very negligible in modern transistors, and we can neglect this. And you will find that most of the hole will go from emitter to collector. And this is very much understandable. If you look at the slope in this region, you can very easily understand why this time the hole is going from base to collector. But if you look at the flow diagram here, you can understand that the flow of hole and the flow of electron is in the same direction in the collector region, which implies that the current due to hole and electron will be in the opposite direction, and that's why the IC will be more or less equal to 0. So you'll find at certain voltage, when you increase the VEC, it actually goes to a point where VEC is equal to 0. Now at certain point you'll find, if you keep on increasing the VEC, your VCB becomes 0, because the forward bias is reducing. It will reduce to a point and will become is equal to 0. So your VCB will be 0 at some point, where your VEC is nothing but your VEB. And at that time, there will be no excess carrier in the collector region. We already have described where the situation where your VCB is equal to 0 and your collector will not have any excess carriers, and the excess carrier concentration in the base region will look something like this, which is more or less linear, and the flow diagram will be something like this. And as your excess carrier concentration in the collector region is now 0, this flow will not be there because there is no excess carriers present. So you'll have an IC, a value of IC, which is nothing but beta IB. So at a point when your VEC is equal to VEB, you'll find the collector current is beta IB. Now let us see what happens after that. In practice, you'll see that actually the current is rising with VEC. There is a slope. So we will describe why it is so. So if your VCB is equal to less than 0, or if your collector junction is in reverse bias, the collector current expression is IC is equal to alpha E plus ICO. Now let us convert the entire expression in terms of IB, and that is why you can replace IE with IC plus IB. This will lead to IC into 1 minus alpha is equal to alpha IB plus ICO, and hence it will be IC equal to beta IB plus beta plus 1 ICO, right? So your IC should be constant when your VCB is less than 0. That means when you increase the VEC to a point, when a collector junction goes in reverse bias, it should be constant. Anyways, your beta plus 1 ICO should be very, very small, because ICO itself is very, very small. We described it. So it should be constant. However, it is not constant in the output characteristics, if you see. So it is not constant with VEC and it has a slope. So the reason behind this slope is your beta actually increases with the increase in VEC. So if your beta increases, definitely your IC also will increase. Now if you look at the excess carrier concentration in this situation, you will find that at reverse bias voltage, the excess carrier concentration in the base region will be something like this. At equilibrium, it is like this red one, and when you increase the reverse bias, your base width, effective base width will start reducing because of the depletion region, because in this case it is very important to consider the depletion region. In the previous cases we ignored it because even after that the situation was more or less explainable, but in this case you have to consider the depletion width, and your depletion width will increase as you increase the VEC beyond this point, and this will lead to a base width modulation, or this will lead to the reduction of base width, that is WB, which actually affects your alpha. And if your alpha gets affected, definitely your beta also will get affected. And it is seen that if your WB reduces, your beta also will reduce. That we will see in the coming discussion. And if your beta if your WB reduces, your beta will increase, not reduce. If your beta increases, definitely your IC also will increase, and that's why you find a characteristics like this. And in the collector region, you will find a very small negative excess current. The concentration will be negative, and this particular concentration is actually responsible for your ICO. Now, in a linear scale, it is very difficult to show this concentration if you draw the entire diagram in scale, because it is very, very small compared to these excess carriers. However, for the representation purpose, I have shown it here. But you should understand that the concentration is very, very small. Now, if you look at the expression of alpha, which is 1 minus WB square by 2LB square minus WB DE divided by LE dB NE, and the expression of beta, which is alpha divided by 1 minus alpha, then you can replace the value of alpha in this expression, and you can very easily find the dependence of WB with beta. Now, in a modern transistor, this particular term is much smaller than this term, and we can consider alpha to be equal to 1 to, in this case for the numerator, to make the entire discussion simpler. So you will come to a point where the expression will become this LE DE NE divided by WB DE NB. So your beta is actually inversely proportional to WB. So beta is proportional to 1 by WB. That is when your WB decreases, your beta increases, and your WB will decrease because of base width modulation. If you increase the VEC, definitely your CB junction will experience a higher reverse bias, and your WB will keep on reducing, and this will actually increase the value of beta. Now, if you find the ratio beta by beta 0 is the value of beta when VCB is equal to 0. Then you can write beta by beta 0 is equal to WB0 by WB, because beta is inversely proportional to beta. So you can write WB0 divided by WB0 minus del XB. Del XB is nothing but the reduction in the WB due to the reverse bias. And this again can be written as 1 divided by 1 minus delta XB by WB. Now this particular term is significant, and hence the change in the IC will also be significant. And that is why you find that with VEC there is a small increase in current even in the active region. However, ideally, the value should be constant as beta IB. You can see from this equation. It should be IC should be is equal to beta IB because there is no dependence of BEC any further. And this term is more or less negligible because ICO itself is very low. I already have shown you that this concentration is very, very small, and this is what is responsible for your ICO. But in practice, you will find that there is a change or increase in IC because of VEC. And that increase you will find because of base width modulation. That is the decrease in the base width due to the increase in VEC, which in turn increases the reverse bias in the collector region. Right? So this is what is the reason behind this increase.
So we have seen BJT circuits in this lecture, 3 different types of BJT circuits: common collector, common emitter, common base, the configuration of these BJT circuits, and then we have seen what is the BJT output characteristics, how the output characteristics of BJT looks like, and what are 3 different regions associated with that output characteristics. One part is known as saturation, another one is cutoff, another one is active region, and why these regions are important. We also sort of discussed which region is important, how do we operate BJT, how do we bias BJT, and so on and so forth. So some of these concepts we already have covered in this lecture. So we will conclude the lecture here, and we will see more concepts associated with BJT and semiconductor physics in the upcoming lectures. Stay tuned. Thank you.